Dear students, welcome to lecture 14 on heterocyclic aromatic compounds. Today we will continue our study of the next heterocyclic compounds, thiophene and imidazole. So thiophene is a compound which can be thought of as resulting from the hypothetical replacement of the sp3 carbon atom in cyclopentadiene with a sulfur, and that will give us a 5-membered cyclic structure with a sulfur as heteroatom, and therefore it is called as thiophene. Now, this thiophene molecule is a liquid at room temperature and boils at 84 degrees Celsius, and it is present as an impurity in benzene, and most of the time it can be detected with indophenyl reaction. Like furan and pyrrole, it is aromatic and has a resonance stabilization energy of around 20 kilocalories per mole. This thiophene ring is present in many drug-like compounds, and here are some of the examples. Olanzapine, which is an antidepressant drug, contains the thiophene ring. So does the suprofen, which is an anti-inflammatory drug, contains a thiophene ring. Some of these thiophene ring containing compounds lead to reactive metabolite formation and toxicity, and there are many other examples of useful drugs which contain a thiophene ring. Now let us move towards the synthesis of thiophene ring. This can easily be synthesized from the reaction between acetylene and hydrogen sulfide. When these gases are passed over a tube of alumina, they react to form thiophene. But it can also be synthesized from the reaction of butane with elemental sulfur at high temperatures and pressure, and it gives us thiophene along with hydrogen disulfide. But thiophene can be synthesized from more easily available organic compounds like succinate, sodium succinate, and phosphorus trisulfide. So phosphorus trisulfide oxidizes the succinate to give us thiophene. Now, as we can expect from an aromatic compound, thiophene does not undergo oxidation or substitution reactions easily in comparison to other thiol containing compounds, but nevertheless S-oxidation is helpful in explaining the toxicity of many drugs. Details of these you can find in these references. Thiophene, because of aromaticity, undergoes electrophilic aromatic substitution mostly at the C2 and C5 positions, and we find that bromination is much faster than in benzene because of its higher reactivity, and dibromination also competes with monobromination. Now let us move towards another heterocyclic compound popularly known as imidazole. This can be thought of as resulting from a hypothetical replacement of the third carbon in pyrrole and giving us imidazole. So this carbon is replaced with nitrogen and we get a structure known as imidazole. This structure of imidazole in solution is actually a hybrid between the following two structures. Here the only difference is that the nitrogen has moved from N1 to N3, and therefore sometimes these structures are also referred to as 1H imidazole and 3H imidazole, but in the unsubstituted ring they are equivalent, and therefore these are known as equivalent tautomers of imidazole. And there is a difference only when you have substituents present on the C4 or C5. Now there are many useful compounds which contain imidazole ring. A simple organic compound known as histamine is responsible for many allergic reactions and is released mostly when we have a itchy feeling. Locally it is released from mast cells. So therefore many drugs have been developed to inhibit the binding of histamine to its receptor, and cimetidine is one of such compounds which is antacid and prevents histamine from binding to the H or H2 receptors. Now imidazole, like other compounds, is also aromatic because it has 6 electrons in the pi conjugated ring structure, and it satisfies Huckel's rule and is thus aromatic. Its resonance stabilization energy is around 22 kilocalories per mole, and its aromaticity can be understood by considering the resonance hybrid structures in which the lone pair on the nitrogen adds the negative charge, and lone pair on this nitrogen participates bonding with carbon, and therefore it has a positive charge. Similarly, charged structures are possible like this. In this, as we have seen earlier, these two structures make a larger contribution because the charge separation is not large as in this case. So that means the positive and negative charges are closely located. So let us now try to understand the acid base behavior of imidazole. N3 nitrogen on the imidazole has a lone pair which is in the plane of the ring. So that means it doesn't participate in the pi conjugation, and therefore it is available for reaction with protons and other acidic substances. And thus the imidazole is basic because of this N3 nitrogen. And it has a pKa value of around 7, which is weakly basic. But in the case of N1, the lone pair participates in the ring resonance present here, and therefore it is less basic, also very weakly acidic because it has a pKa of around 14.5. Thus imidazole is many times referred to as being amphoteric because it can show either basic or acidic behavior based upon the conditions. Now let us move towards the synthesis of imidazole. Imidazole and its derivatives can be synthesized from the alpha dicarbonyl compounds when these are reacted with ammonia and aldehyde. So alpha dicarbonyl compounds, when they are reacted with 2 moles of ammonia and aldehyde, we form substituted imidazole derivatives. Imidazole itself can be formed by the reaction of tartaric acid with formaldehyde and ammonia. So tartaric acid, first it is nitrated, and this oxidation leads to the formation of this dicarbonyl compound, which is reacted with formaldehyde and ammonia to give us imidazole. Now let us see some of the reactions of imidazole. As expected, because of its aromaticity, it will undergo nitration and electrophilic aromatic substitution reactions. But generally these nitrations happen at the 4th or 5th position, but mostly being favored at the 4th position. So nitration of imidazole will give us 4-nitroimidazole as the main product. Imidazoles are brominated easily. So imidazole, when reacted with bromine in acetic acid and sodium acetate, will result in the tribromination. These two bromines can be selectively removed by treatment with sodium sulfite and water, and slightly heating the reaction mixture. It will give us 2-bromoimidazole. Acylation of imidazole is also possible, but it gives us 2 acyl derivatives exclusively, and these acylations can be performed under mild conditions. This is thought to proceed through first N-acylation, where imidazole first reacts with benzoyl chloride, and N-acylation at the N-nitrogen position takes place, where this nitrogen gets a positive charge. When you heat this reaction mixture further, a rearrangement of the acyl group takes place from nitrogen to carbon in electrophilic aromatic substitution, and both positions are benzoylated. When the N-benzoyl derivative is then hydrolyzed in the presence of water to give us the 2-acyl derivative. So in the next lecture we will see